Welcome viewers, this is my third lecture on linear algebra. In earlier two lectures we have discussed vector spaces and subspaces. This lecture is about linear independence and dependence. We have already defined spanning set of a vector space V as a set W consisting of n vectors alpha 1, alpha 2, alpha n such that every vector in V can be expressed as a linear combination of vectors of W. For example, W1 consisting of three vectors 1 0 0, 0 1 0 and 1 1 1, it can spans R3 the vector space. You can check that all the vectors in R3 can be expressed as a linear combination of these vectors 1 0 0, 0 1 0 and 1 1 1. We can have another exercise in which another subset W2 consisting of 1 1 0, 0 1 0, 1 1 0 and 1 1 1 also spans R3. Viewers can check that they actually represent any vector. In fact, any linear combination of this vector can be a vector space in V. Not only this, any vector V in V can be expressed as a linear combination of these vectors. So, W1 and W2 both spans R3. This is not all. You can have another subset W3 consisting of different set of vectors 1 0 0, 0 1 0, 0 0 1, 1 1 1 and 1 1 0 spans R3. This can also be checked. In fact, one may notice that there are number of subsets which can span the vector space V. So, there may be sets W1, W2, Wm spanning vector space V. Now, the question is, can we find a minimal spanning set? For this, we will be giving some definitions first and then some results. So, the first definition says that the set of vectors S consisting of alpha 1, alpha 2, alpha n in a linear vector space V is linearly independent if the linear combination of these vectors, that is C1 alpha n, C1 alpha 1 plus C2 alpha 2 plus Cn alpha n is 0 provided all the scalars C1, C2, Cn are 0. So, if this is possible, then the vectors are linearly independent, otherwise the vectors in S will be linearly dependent. By this I mean to say that the set S has linearly dependent vectors if there exists some non-zero Ci's for which the linear combination 1 is 0. The vectors are linearly independent or dependent. We need to find the solution of this equation, that is C1 alpha 1 plus C2 alpha 2 plus Cn alpha n is equal to 0. So, if you find a trivial solution of the equation in which C1, C2, C3, Cn all are 0, then the vectors are linearly independent. So, if such a solution is possible, then the vectors are linearly independent. However, if one or more of the C's are non-zero, then the set S is linearly dependent. We can take some examples to illustrate this. So, let us say we have a set S consisting of 1 0 0, 0 1 0, 0 0 0 1. We have to see whether this set is linearly independent or dependent. Now, to consider for this, we consider the linear combination C1 1 0 0 plus C2 0 1 0 plus C3 0 0 1 and this right hand side is equal to 0. So, let us consider this linear combination and set it to 0. If we can find a solution of this which is trivial solution, then we say the vectors are linearly independent, otherwise the vectors are linearly dependent. Now, one can notice that these will give rise to 3 equations if you compare component wise. So, only this component C1 into 1, this is not contributing, this is not contributing. So, if we equate it to 0, so C1 is equal to 0. In the second, only this is contributing, C2 into 1, others are not contributing. So, C2 is equal to 0, and the third component gives us C3 equal to 0. So, this is the only solution possible for this equation to be satisfied, and that is why we say that the set S consisting of these 3 vectors is linearly independent. So, S is linearly independent set of vectors. Now, in another example, we have to check whether the set 0 1 1 0 minus 1 1 is a set of linearly independent or dependent set of vectors. The solution is, we consider the linear combination of these 3 vectors. The combination is C1 0 comma 1 plus C2 1 0 plus C3 minus 1 equated it to 0 comma 0. We equate component wise. So, this will not be contributing, but this will give us C2 minus C3 is equal to 0, and the second component gives us C1, this will not contribute, minus C3 equal to 0. So, we have 2 equations in 2 unknowns C1, in 3 unknowns C1, C2 and C3. So, the solution of these 2 equations gives us C2 is equal to C3, the first equation, C1 is equal to C3 from the second equation, and this can assign any, this can be assigned any arbitrary value k. So, we will have C3 is equal to 1, C2 is equal to 1, C1 is equal to 1 when k is equal to 1 is the solution of this equation. So, a non-trivial solution is possible. So, there exists a non-trivial solution of the given system, and hence we say the 3 vectors 0 1 1 0 minus 1 in the set S are linearly dependent, or the set is the set of linearly dependent vectors. Now, we are now in a position to make some remarks. So, the remark 1 is that the set S consisting of a singleton 0, which is additive identity in the vector space, is linearly dependent in any vector space. So, whatever be the vector space, this singleton set will be linearly dependent set, and this can be proved very easily. You can see that C1 into null vector theta is equal to null vector for any value of C1 other than 0. So, the non-trivial solution for this equation exists, and that is why this set is always linearly dependent. In another remark, the set of 2 vectors alpha 1 and alpha 2, if it is linearly dependent, then one of them is a scalar multiple of the other, and we say that alpha 1 and alpha 2 are collinear. This is written, this is proved here. We will have C1 alpha 1 plus C2 alpha 2 is equal to null vector, where C1 and C2, if it is C1 is not 0, then one can write alpha 1 is equal to minus C2 by C1 times alpha 2. So, alpha 1 is written in terms of alpha 2 if C1 is not 0. Of course, if C2 is not 0, then you can write down alpha 2 is equal to minus C1 by C2 into alpha 1. So, this way we can say that the 2 vectors are collinear. Similarly, the set of 3 vectors alpha 1, alpha 2, alpha 3 is linearly dependent if one of them is a linear combination of the other 2, and in such a case we say that the vectors alpha 1, alpha 2, alpha 3 are coplanar. Like I have written, alpha 1 is equal to A times alpha 2 plus B times alpha 3. Now, some examples: the vectors 0 1 comma 1, 1 comma 0 comma 1 and 1, 1, 2 are coplanar. Let us see, we can write down the third vector 1, 1, 2 as a linear combination of the first two vectors 0, 1, 1 and 1, 0, 1. You can see this is 1, so we will have 1 on this side. The second is 1, we will have 1 here, and this 1 plus 1 is 2. So, 1, 1, 2 is a linear combination of these two vectors, or we say the three vectors 0, 1, 1, 1, 0, 1 and 1, 1, 2 are coplanar in this case. Another remark is the linear dependence of a set of two or more vectors in a vector space means that at least one of the vectors can be expressed as a linear combination of the other vectors. Now, this we write down in the form of a theorem. Let S consisting of n vectors, n is greater than or equal to 2, be a set of vectors in a vector space V, then S is linearly dependent if one of the vectors in S can be expressed as a linear combination of the rest of the vectors. Now, to prove this, we have given a set S as linearly dependent, then there are constants C1, C2, C3, Cn, some of which are non-zero. So, we will have C1 alpha 1 plus C2 alpha 2 plus Cn alpha n is equal to null vector. So, this is what we have from the very definition of the dependent set S. Now, we consider Ck to be non-zero. Since all of the Ck's are not 0, so let us say Ck is not 0, then Ck alpha k is equal to minus C1 alpha 1 minus C2 alpha 2 minus Ck minus 1 alpha k minus 1 minus Ck plus 1 alpha k plus 1 up to minus Cn alpha n. So, what I have done is I have taken Ck alpha k on one side and rest of the vectors on the other side. And since Ck is not 0, so I can divide the whole equation by Ck. So, alpha k is equal to minus C1 by Ck alpha 1 minus C2 by Ck alpha 2 and up to Cn by Ck alpha n. And since minus C1 and Ck they are constants, so I can recall them to be B1 and minus C2 by Ck as B2 and so on. So, I can express the vector alpha k as B1 alpha 1 plus B2 alpha 2 plus Bk minus 1 alpha k minus 1 up to Bn alpha n. By this I mean to say that I have expressed alpha k as a linear combination of alpha 1, alpha 2, alpha k minus 1, alpha k plus 1 up to alpha n. That is, alpha k is expressed as linear combination of rest of the vectors. That is how we prove the theorem. Then some simple results are stated in the form of theorems. The first theorem is any subset of a linearly independent set is also linearly independent, and the second is that any subset of linearly dependent set is also linearly dependent. Now, these are the two exercises user can themselves try. Now, I consider the set R2 can be spanned by the sets S1 consisting of two vectors, S2 as another two vectors and S3 consisting of the set of three vectors 0 1, 1 0, 1 comma 1. This can be easily verified, like if I consider for the set S1, then any vector AB in R2 can be expressed as a linear combination of the vectors of this set 0 1 and minus 1 1. So, it is C1 0 1 plus C2 minus 1 and 1. If we can solve it, then C1 is equal to A plus B and C2 is equal to minus A. So, we can say, since we can find out C1 and C2 in terms of known vectors A and B, that means this S1 can span R2. If you consider the set S2 in the next example, then AB is equal to C1 1 comma minus 1 plus C2 minus 1 0. So, any vector AB in R2 can be expressed as a linear combination of these two vectors. You can solve the two equations. C1 is equal to minus A and C2 is equal to minus A plus B is a solution. So, given AB, we can find out C1 and C2, so that the vector AB can be expressed as a linear combination of given two vectors. So, we can say that this set R2 can be set, or maybe vector space R2 can be spanned by this set. Similarly, to see that S3 spans R2, we again consider any vector in R2 expressed as linear combination of given vectors. So, in this case we find that C1 is equal to B minus K, C2 is equal to A minus K and C3 is equal to K, where K is an arbitrary value. The idea in this case is that we have two equations in 3 unknowns. So, that is why we have to introduce an arbitrary constant K over here, and that means there will be, you can choose the value, you can assign the value to this constant K and will be having different solutions. So, in this case number of solutions are possible, and you cannot express AB in a unique manner in this case. And also another observation here is that more than one spanning set for R2 is possible. On the basis of this, we can make some remarks. One can notice that the sets S1 and S2 are linearly independent, while the set S3 is linearly dependent. Also, any vector in R2 can be expressed uniquely in terms of vectors of S1 and S2, that we have observed. But if we consider the third set S3, then this is not true, because the vector, if we consider a specific vector 2, 5 belonging to R2, can be expressed as linear combination of these vectors in many different ways. These are some of the ways you can find out. You can express 2, 5 is 4 times 0, 1 plus 1 times 1, 0 plus 1 times 1, 1. Further, 2, 5 can also be expressed as this. Also, 2, 5 can be expressed as 6, 0, 1 plus 3, 1, 0 minus 1, 1. This is also possible because there is arbitrary constant K appearing in the solution of the linear combination. That is why we are having this particular situation. So, on the basis of this, we say that the independent set of vectors spans the vector space uniquely, while if we have a dependent set of vectors, then any vector cannot be necessarily represented as linear combination of given vectors. For dependent set of vectors, a vector in the spanning subspace can be expressed in many different ways. So, this is another remark. And finally, if it is desirable that a vector can be expressed as a linear combination of given vectors uniquely, then the vectors in the set, in the spanning set, must be linearly independent. So, this is the observation. On this basis, we define basis for a vector space V. So, this is a definition. A linear independent set S, which is a subset of V, that can span the vector space V, is called the basis for V. Now, this is the definition for basis. Example: show that the set S consisting of 1, 1 and 2, 3 is a basis for R2. Now, to establish this, what we have to do is, we have to show two things. One is that S is independent, and the second is S spans V. You can look at the definition. We have to have a linearly independent set, and then it should span V. So, these two things have to be there. So, let us first check the linear independence of the set. Again, what we have to do is we have to form the linear combination of the given set C1 1 comma 1 plus C2 2 comma 3 and equate it to 0. And let us see what we have next. C1 plus 2 C2 is equal to 0 and then C1 plus 3 C2 equal to 0. So, we have two equations and two unknowns and the solution is C2 is equal to 0. If you subtract the 2, we will have C2 equal to 0, and if you substitute C2 is equal to 0 say in this equation, then C1 equal to 0. So, this system will have only one solution and that is the trivial solution C1 equal to 0 and C2 equal to 0, and this establishes that S is independent set. The second thing we have to show for the basis is that S spans V. For this we consider a linear combination C1 1 comma 1 plus C2 2 comma 3 and we show that any vector AB in V can be expressed as this combination. So, if we can find out the solution for this equation then it is possible, otherwise not. So, let us try to solve this system. So, what we have is C1 plus twice C2 is equal to A and the second component gives us C1 plus 3 times C2 is equal to B. If you solve this, you subtract the 2, it is C2 is equal to B minus A, and if you substitute it here, then C1 comes out to be 3A minus 2B. So, given AB, you can find out C2 from this equation and C1 from this equation, and this solution will be unique. So, we can say that S spans V, and that establishes that we have a basis for the given vector space. Now, the next theorem will say that S is a set consisting of n vectors, then let S be a basis for a vector space V, then the vector V, any vector V in V can be uniquely represented as a linear combination of vectors of S. So, if we have a basis, then the vector V in V can be uniquely represented as a linear combination of vectors of S. Now, to prove this, let the vector V in V can be represented as a linear combination of vectors in two different ways. So, we write down V as C1 alpha 1 plus C2 alpha 2 plus Cn alpha n. At the same time, we have another coefficient C1 dash, C2 dash, Cn dash, etc. So, that V is C1 dash alpha 1 plus C2 dash alpha 2 plus Cn dash alpha n. So, if this is possible, then we can write down, we can multiply the second equation by minus 1. So, we will have minus V is equal to minus C1 dash alpha 1 minus C2 dash alpha 2 minus Cn dash alpha n. So, if we add the two equations, what we have is V plus is times minus V is equal to null vector. This is the definition of, this is the property of the vector V and theta, null vector theta. Then C1 minus C1 dash alpha 1 plus C2 minus C2 dash alpha 2 times alpha 2 plus the last term is Cn minus Cn dash alpha, Cn minus Cn dash times alpha. So, this is equal to theta. Now, we know that alpha 1, alpha 2, alpha n vectors are linearly independent. So, these coefficients have to be 0. That is the property of, that is the basic requirement for the independent set of vectors. So, this is 0, this is 0, this is 0. So, C1 minus C1 dash is equal to C2 minus C2 dash is equal to Cn minus Cn dash, all equal to 0, and if you further simplify, then C1 is equal to C1 dash, C2 is equal to C2 dash, and finally Cn is equal to Cn dash. So, all C1 Ci's are equal to corresponding Ci dash, and that means they are not different. So, what we can say is there is only one representation possible. We have started with two different representations, but ultimately they come out to be the same. So, we say the representation is unique. So, this establishes the theorem. Now, we have another theorem which says that the null vector theta belonging to S, which is a subset of V, then S is linearly dependent set. By this I mean to say that if there is a null vector in the set S, then set S is linearly dependent set. So, any set containing theta is linearly dependent. That is another way of writing this theorem. So, let us try to prove this. We consider a set of n plus 1 vectors alpha 1, alpha 2, alpha n, which are non-zero, and then we add another vector theta into this set. So, let us consider whether this set is linearly independent or not. Now, to prove that this set is linearly dependent or independent, I have to consider this linear combination. So, C1 alpha 1 plus C2 alpha 2 plus Cn alpha n plus Cn plus 1 theta is equal to the null vector theta. Now, I consider C1 is equal to C2 is equal to Cn is equal to 0 and Cn plus 1 is equal to k. Now, this choice is possible. So, if I consider Cn plus 1 is equal to k and all this is non-zero, all this is 0, k is not 0, then C1 alpha 1 plus C2 alpha 2 plus Cn alpha n plus Cn plus 1 theta is equal to 0. Why? Because C1 0, so this term is not contributing, C2 is 0, so this is not contributing, similarly this is not contributing. What remains is only this term Cn plus 1 into theta. So, whatever be Cn plus 1, even if it is not 0, Cn plus 1 into 0 is 0. So, I have found one solution in which all C1s, all Cn's are 0, but Cn plus 1 is not 0. So, I have found one non-trivial solution for this to happen, and that is why we have this set alpha 1, alpha 2, alpha n theta as linearly dependent set. So, therefore, non-trivial solution exists and it is linearly dependent set. Remark: a set S containing theta cannot be a basis for a vector space. So, this is one observation which can directly derive from the earlier theorem, because by the very definition of basis, the set S has to be linearly independent, only then it can be a basis for a vector space. Now, since S containing theta will be linearly dependent whatever be the vector space, so it cannot form a basis for a vector space. So, this is about this remark. Then the 0 vector space theta has no basis. So, if we consider this set, this is always linearly dependent. So, this cannot form a basis, it has only one set in this. So, we also know that this set consisting of only theta forms a vector space. So, this vector space has no basis. This is another remark. The next theorem says that if S is a set consisting of n vectors and is a basis for the vector space V, then if you add one more vector alpha in this set and we have another set S dash consisting of alpha, alpha 1, alpha 2, alpha n and still is a subset of V, then this S dash cannot be a basis for V. So, if we have a set S which is a basis for the vector space V, then adding one more vector in S dash cannot be a basis for V. Now, to prove this, let S be a basis. So, it has to be a set of independent vectors spanning V, that is the definition for basis. And let us say we have another vector alpha which belongs to S dash. Since alpha also belongs to V, S dash being a subset of V, then alpha can be expressed as a linear combination of alpha 1, alpha 2, alpha n. That is the very definition of basis. Any vector alpha in V must be expressed as a linear combination of vectors of the basis. So, alpha can be expressed as a linear combination of alpha 1, alpha 2, alpha n. By this I mean to say is that alpha is equal to C1 alpha 1 plus C2 alpha 2 plus Cn alpha n, where all Ci's are not 0, and that means C1 alpha 1 plus C2 alpha 2 plus Cn alpha n minus alpha is equal to 0. That means alpha, all Ci's are not 0, some of them may be 0, but all of them are not 0. So, this set alpha, alpha 2, alpha 1, alpha 2, alpha n together with this alpha is linearly dependent set. So, there exists a linear combination in which we have a non-trivial solution possible. So, this set cannot be linearly independent, and if this is not linearly independent, then this set S dash cannot be a basis for V. That is what the theorem is. And secondly, if we have S double dash, which is a subset of S, cannot be a basis for V. So, we prove this by contradiction. So, let us assume that S double dash be a basis for V. If S double dash be a basis for V, S double dash is a subset of S. So, let alpha 1 belongs to S, but not to S double dash, because S double dash is subset of S, there must exist some alpha 1 which belongs to S, but not to S double dash. So, we will have alpha 1 belonging to S, but not to S double dash. Then alpha 1 can be expressed as a linear combination of S double dash. So, alpha 1 can be expressed as a linear combination of vectors of S double dash. By this I mean to say that alpha 1 is equal to C2 dash alpha 2 plus C3 dash alpha 3 plus Cn dash alpha n, because S double dash is a basis for vector space V, and alpha 1 belongs to V. It may not belong to S double dash, but it belongs to V. So, V, any vector in V can be expressed as a linear combination of these vectors. So, alpha 1 is equal to C2 dash alpha 2 plus C3 dash alpha 3 plus Cn dash alpha n, where all of them need not be 0, or there may be some non-zero value C of these coefficients for which this is possible. Thus, we conclude that all coefficients are not 0, or C1 dash alpha 2 plus C3 dash alpha 3 plus Cn dash alpha n minus alpha 1 is equal to 0 if we take alpha 1 on the same side, and by this S is equal to alpha 1, alpha 2, alpha n is a basis for V. Since a basis, so C2 dash, C3 dash, Cn dash all has to be 0, because only then it will be a set of independent vectors, and this is set of independent vectors because we have already assumed that S is a basis for V. So, now we have arrived at a contradiction. Alpha 1 is not a linear combination of vectors of S double dash, and that means S double dash cannot span V, or S double dash is not a basis, and that is how we prove the theorem by contradiction. Then next is the remark: the number of vectors in a basis is unique. That is, if the basis S for the vector space V has n vectors, then every other basis for V also has n vectors. In fact, in my earlier two theorems, one theorem says if I have more than one vector, then again it will not form a theorem, it will not form a basis, it becomes linearly dependent. If I have one less vector, then again it will not span the vector space. So, n is fixed for a basis to have n vectors for a vector space V. There may be more than one basis for a vector space, but the number of vectors in the basis is unique. So, this is what the remark is, and on the basis of this we can now define the dimension of the vector space. We say that the number of vectors in the basis for a vector space is the dimension of the vector space. If a basis S of a vector space V has n vectors, then the dimension of vector space V is n, or we write as dimension of V is equal to n. Therefore, there may be number of bases for a given vector space are 3, like we will have 1 0 0, 0 1 0, 0 0 1 is a basis for R3. We can have another basis 1 0 0, 0 1 0, 1 1 1 is also a basis for R3, 1 0 0, 1 1 0, 0 0 1 is also basis for R3. So, there may be number of bases for a given vector space R3, but the number of vectors in each basis is fixed. This basis also has 3 vectors, this basis also has 3 vectors, this basis also has 3 vectors, or we say R3 has dimension 3. So, out of these many bases, R3 has a standardized basis or a natural basis as 1 0 0, 0 1 0, 0 0 1. It is also denoted as E1, E2, E3. E1 is the vector in which the first component is 1, rest of them are 0. E2 is the vector in which the second component is 1, others are 0. E3 has the third component 0. So, this is the natural basis for R3. So, R3 may have number of bases, each consisting of 3 vectors, but this special basis, this basis has a special name, we call it standardized basis or natural basis. So, we will have a natural basis and there may be other bases for a given vector space R3. Another definition, a vector space V is called finite dimensional if there is a finite subset of V that forms its basis. If no such basis exists, then the vector space V is called infinite dimensional. On the basis of this, we write down a theorem. It says that let W be a subspace of an n dimensional vector space V, and if WR, which is consisting of R vectors x1, x2, xr is a basis of W, then there exist vectors xr plus 1 xn up to xn in V such that x1, x2, xr plus 1 xn is a basis for V. Now, what we have stated in this theorem is that we have a subspace of an n dimensional vector space V. Since a subspace, so it may have less number of vectors than n. So, this has R vectors x1, x2, xr, then this basis can be expanded to include more vectors from V, then this forms a basis for V. So, we have a basis for subspace, we can extend it to form a basis for V, that is the theorem. So, let us try to prove this result. Now, if R is equal to n, then WR is a basis for V. Actually, it is a trivial case because we do not have to add anything into WR to form a basis for V. Now, consider the case when R is less than n. So, for this we assume a basis for V as W1 consisting of exactly n vectors y1, y2, yn. Now, we add these vectors into the set S1. So, now S1 is x1, x2, xr, the basis for WR, and y1, y2, yn. Now, we try to make this S1 as a basis for V. Actually, this will span the set V, but it may not be a basis. Basis will be when we have exactly n linearly independent vectors in S1. So, we try to obtain linearly independent vectors out of this set, so that it forms a basis. Now, to method is we consider the set of vectors x1, x2, xr and y1 only. So, we add only one vector at a time in this set. So, x1, x2, xr, y1, and we say whether these set of vectors are linearly independent or not. So, we check whether this is linearly independent or not. If y1 together with this is linearly independent, then we add y1 in S1, else we delete y1 from this. So, we will have y1 in this set only when this set forms a linearly independent set, otherwise we delete y1. We repeat this by adding y2, y3 one at a time into the set S1. So, we repeat this process with y2, y3, yn. So, the total vectors in S1 after this step will be m, say, then m will be greater than equal to n. But m greater than n is not possible for an n dimensional space, because n dimensional space will have at the most n independent vectors. So, m is equal to n is the only possibility, and in that case we say S1 will be a basis for V. So, that is how we have extended the set S1 to form a basis for V. Now, if we have a vector space V which is finite dimensional, then dimension of W is less than equal to dimension of V for every non-zero subspace W of V. So, every subspace W of V will have dimension less than equal to dimension of V, and in a special case, when dimension of W is the same as dimension of V, then we say this W will be the same as the vector space V. I suggest that viewers can prove this results. The second one is, let S is a set of linearly independent vectors, then there exists a basis W for V such that S is a subset of W. The next remark is, the dimension of a vector space consisting of only of null vector is 0, because if we have this space has only 0 vector. So, 0 vector is always linearly dependent. So, we will have its dimension as 0. Now, we talk about the fundamental problem of linear algebra, which is given in two different forms. The form 1 suggests that given vector space V, if we select vectors to form a basis for V. The second form is, construct basis from given set S which is a subset of V. So, these are two different forms. So, let us try to see with the help of an example. So, extend the set S to form a basis for R3. You can notice that R3 is a 3 dimensional. Why it is 3 dimensional? Because in one of my earlier examples I have considered a natural basis for R3 which consists of 3 vectors. So, every basis, there may be number of bases for R3, but each basis will have 3 vectors. Now, we have a set S which consists of only 2 vectors. So, if these 2 vectors are linearly independent, then we have to add one more vector from R3, so that this forms a basis. So, this is how the solution works. So, we first check the linear independence of S. If these 2 vectors are independent, then we have to form a basis. We have to add one more vector into it to form a basis. So, first check the linear independence of the set S. We consider the linear combination to be 0, C1 dash 102 plus C2 dash 114 is equal to 0, 0, 0, and then from this we get C1 dash plus C2 dash is equal to 0 from the first component, C2 dash is equal to 0, and we will have 2 C1 dash plus 4 C2 dash is equal to 0. So, C2 dash is 0. So, from this C1 dash is 0, and then from this C3 dash is 0. So, this will have only a trivial solution possible. So, we can say that the vectors 102 and 114 in the set S are linearly independent. So, to form it to be a basis for R3, we have to add one more vector. So, one vector from R3 must be added in S, so that the extended set forms a basis. The 3 vectors must be linearly independent and must span the vector space. This is the condition for the basis. So, what we do is we add a vector x1, x2, x3 in this. So, we consider the span of all the vectors of this set S. So, let us say x1, x2, x3 is a vector in the span of S. So, x1 comma x2 comma x3 is equal to C1 102 plus C2 114, and that means if we if we equate component wise, then x1 is equal to C1 plus C2, x2 is equal to C2 and x3 is equal to C twice C1 plus 4 times C2. If we solve these three equations, we will have C2 is equal to x2, C1 is equal to x1 minus x2 and x3 is equal to twice x1 plus twice x2. That means any vector of the form x1 x2 comma twice x1 plus twice x2 can be obtained as a linear combination of vectors of S. Now, if I consider this vector 1, 2, 3 which clearly belongs to V, then it cannot be expressed as a linear combination of vectors of S, because we cannot write down, because this vector 1, 2, 3 is not in this form. x1 is 1, x2 is 2, but 2x1 plus 2x2 is actually is not 3. That is why 1, 2, 3 does not belong to the span of S, and that is why 1, 2, 3 is independent, then independent vector, and that means we can add this vector in the set S, and what we have is 1, 0, 2, 1, 1, 4 union 1, 2, 3 is a linearly independent set of 3 vectors. So, we can add this vector into the set S, we form another set B, and now we have set of 3 independent vectors, and this spans the vector space R3 also. One can check very easily, and then we can say that it forms a vector space. Verify that 1, 2, 3, 1, 0, 2, 1, 1, 4 is a basis for V. So, we can consider any arbitrary vector in V, x1, x2, x3, and try to express as a linear combination of these 3 vectors. These are 3 equations if you equate component wise, and one can solve these 3 equations. So, this is the solution which I have obtained. You can verify that this is actually the solution of this, and that means 1, 0, 2, 1, 1, 4 and 1, 2, 3 forms a basis for R3. Remark: any vector not in the span of S can be included in S to get the basis for V. I have taken 1, 2, 3 in this set to form a basis, but any other vector can be taken instead of this vector, and that will be a basis. Only condition is that this third vector should not be in the span of these 2 vectors. That means basis is not unique. In the next example, I will consider these vectors W is equal to 0, 1, 2, 1, 1, 0, 2, 3, 2, 1, 3, 4. Find the basis for SW. Now, in this example, I have 4 vectors in this set W, and I have to find the basis for span of W. It is a 3-dimensional, W is a subset of R3 because all the vectors belongs to R3. So, we have to form the basis for span of W. What I have to do is, I will see one by one whether they are independent or not. So, starting with 0, 1, 2 in W1. So, 0, 1, 2 is always independent. So, it may be extended to form a basis. We consider another, we include another vector 1, 1, 0 from this set in W2, and let us check whether this forms a basis or not. Again, the procedure is same, you have to find the linear combination, and if you solve this, we will find that C1 is equal to C2 is equal to C3 equal to 0 is the only solution possible for this, and that means this also is set of linearly independent vectors. Again, we repeat with the third vector 0, 1, 2, 1, 1, 0 and 2, 3, 2 is the W3, and whether and then we check whether they are linearly independent or not. So, we consider C1 0, 1, 2 plus C2 1, 1, 0 plus C3 2, 3, 2 is equal to 0, 0, 0 as a linear combination, and solving it we will have these 3 equations, and the solution for this is C1 is equal to minus C3 and C2 plus twice C3 is equal to 0, and this means C1 is equal to 1, C2 is equal to 2, C3 is equal to minus 1 is the solution for this, and that means W3 is linearly dependent set. So, these two are linearly independent, but when we add this, so then this becomes linearly dependent set. So, this cannot form a basis. So, I will drop this. Instead, I consider this vector 1 3 4 is also, and one can check whether it is linearly dependent or not. So, if I write down 1 3 4 on one side and 1 1 0 and 2 times 0 1 2 on the right hand side, then I can see that 1 3 4 can be expressed as the linear combination of these two vectors. So, even this set is not linearly independent. So, in the given set we have only two independent vectors and rest of them they form linearly dependent set. So, this is, so span of W is of dimension 2. So, SW is span of W2, the same as span of W2. Now, for SW is for SW basis is W2 is 0 1 2 and 1 1 0. So, this is the basis. Now, the set W cannot span R3 because R3 is 3 dimensional and any basis must have 3 basis must have 3 vectors. So, the set W cannot span R3. So, if we have to find a basis for R3, then we have to add one more vector into this, so that we have a basis. So, let us try to extend this set to have one more vector into it, so that it forms a basis for R3. So, what I do is I consider 0 1 2 and 1 1 0 and find the span of this set. So, let us say alpha belongs to span of W, that is alpha belongs to SW, then any vector in this will be of this form. So, C1 0 1 2 plus C2 1 1 0 will be of the form C2 comma C1 plus C2 comma twice C2, and that means basis for R3 is 0 1 2 comma 1 comma 0 and one more vector 1 5 1, which is not of this form. 1 5 1 is not of this form. Note that 1 5 1 is not of this form C2 comma C1 plus C2 comma twice C1, and that means this cannot be generated by this, and that means this is independent. So, now I have 3 vectors which forms an linearly independent set, and that means this may be a basis for R3, and any linear combination of these 3 vectors will span R3. At the end, let me summarize what we have done today. I have started with the spanning set. The idea was to introduce the concept of linear independence and dependence, and then we have given the definition, and then we have taken some examples, then we have established certain results, and on the basis of those results we have tried to show that how a given set of linearly independent vectors can be extended to form a basis for an n dimensional space. Thank you.
Thank you.